Bismillahirrahmanirrahim. We continue our discussion in software design concepts and principles and start the discussion from where we have left in the previous lecture. Before proceeding ahead, let's have a recap of the topics within this chapter that we have already discussed. We have an introduction on what is a design and who is responsible to develop software designs. Then we develop a relationship between the software design and software engineering, how software design is a phase within software engineering, and we discussed there are 4 different types of sub-design phases within software design. That includes data design, architectural design, interface design, and component level design. So the 3 models that have been generated from the requirements analysis phase are then converted into respective these 4 types of designs. Then we discussed the design process, in which the quality aspect within software design has been discussed. Different quality parameters which are related to a software needs to be incorporated in the software design, and we discussed in detail those quality parameters. Then we discussed, or we were discussing actually, different sub-phases of software designs, in which we discussed the data design, that is how data can be given a structure in terms of using some data structure or generating different types of diagrams that brings a relationship among different data objects. Then we discussed the architectural design, in which different architectural styles have been used for the information flow within the design. We were then discussing the interface design. Different types of interfaces are there, but the interface that is the focus of this particular subphase is the user interface. So we discuss the user interface. What is user interface? It is the mechanism in which user communicates with the software or the computer system. In this particular subphase, we discussed some golden rules, how we can design a good user interface which is quite user friendly using those golden principles. Then we discuss what is the user interface design, in which we have to develop different types of models. Now these models may not be on computer, they may be on paper. In these models, 4 different types of models have to be created depending on the user profiles. So 4 different types of models are created, and the 4th model, which is the system model, in which we have to develop the prototype for the system that is going to be built. The user interface design process have been then discussed next, how the process continues to design the user interface. And we discussed 4 different activities in the user design process, user interface design process. The first activity was to understand the users who are going to use the interface, their task, what tasks they are going to perform with the interface, and the environment in which the interface will operate or the software will operate. We have to analyze and develop models for these 3 entities. In second activity, we then design the user interface. That means the conversion of user perception into the system model, into the reality. So this is the interface design, again a paperwork. The third step is the construction of user interface, in which you have to use some tool the construction tool to construct the interface. This is basically developing a prototype for the user interface. And the fourth and final activity is the evaluation of interface evaluation that we can call. In this, we have to then test and review, validate and review the prototype that have been developed and understand if the interface is easy to use for different types of users, if it is not putting burden on user memory, if the interface is acceptable to the user, and how the user perception has been implemented into the practical prototype. So these were the points that we had already discussed in the previous discussions. Now let's proceed with today's discussion. We will continue our discussion in the user interface design. In today's discussion, we are going to see some of the design issues. These are the common design issues which a software engineer generally face while designing the user interface. These are the issues which are also faced by the user of the user interface and also the designer or the software engineer who are responsible to design the user interface. So let's proceed with the discussion and see what are the common design issues. As the design of the user interface evolves, 4 common design issues almost always surface. These are the system response time. We are going to discuss them in detail now. The second one is the user help facilities. Third one, error information handling. And the fourth common issue that is being faced is the command labeling. Unfortunately, many designers do not address these issues until relatively late in the design process. Unnecessary iterations, project delays, and customer frustration is then generally the result. It is far better to establish each design issue as a design needs to be considered these issues at the beginning of the software design when changes are easy and costs are relatively very low. So let's now move on to discuss the first design issue, which is the system response time. System response time is actually the primary complaint for many interactive applications. In general, some system response time is measured from the point at which the user performs some control action. For example, hits the return key or clicks a mouse until the software responds with desired output or action. So this is the time user clicks or hits an object with the key and the time the system generates a response for the user action. System response time has 2 important characteristics, which are the length of the response time and the variability of the response time. If the length of system response is too long, user frustration and stress is quite visible. However, a very brief response time can also be detrimental if the user is being paced by the interface. So very quick response time is also not acceptable, while delayed response times are also not acceptable for the user. A rapid response may force the user to rush and therefore may make mistakes. So Rapid responses and delayed responses, the length should be taken into consideration. Very rapid response is not acceptable and delayed response time is still not acceptable to the user. While the other characteristics, the variability, that refers to the deviation from average response time, and in many ways it is the most important response time factor. Low variability enables the user to establish an interaction rhythm even if response time is relatively long. For example, a 1-second response to a command is preferable to a response that varies from 0.1 to 2.5 seconds. That means the length or response time length should be fixed. It should not variate. The user is always off balance, always wondering whether something different has occurred behind the scenes. So you need to fix the length of the actions. If some actions are generated, some responses of some actions are generated quick and some are getting delayed. So this is creating frustration for the user. So there has to be the specific duration for the response in response to some action, so that user must be aware that this particular action would take this much time for the system to generate the response. The second design issue is the user help facilities. Almost every user of an interactive computer-based system requires help now and then. In some cases, a simple question addressed to a knowledgeable colleague can do the trick. In others, detailed research in a multi-volume set of user manuals may be the only option. In many cases, however, modern software provides an online help facility that enables a user to get a question answered or resolve a problem without leaving the interface. So two different types of help facilities are generally encountered in software system, that is the integrated help and the add-ons. An integrated help facility is designed into the software from the beginning. It is often context sensitive, enabling the user to select from those topics that are relevant to the actions currently being performed. Obviously, this reduces the time required for the user to obtain help and increases the friendliness of the user interface. While the add-on help facility is added to the software after the system has been built. In many ways, it is really an online user's manual with limited query capability. The user may have to search through a list of hundreds of topics to find appropriate guidance, often making many false starts and receiving much irrelevant information. There is little doubt that the integrated help facility is preferable to the add-on approach. So, in integrated help facility, user is guided through his actions, what next appropriate action would be required by the user. So a list of actions are suggested by the system and user can then select the appropriate one. For example, when you click the spell checker in word processor, so for a particular word, different options are available. So whatever suits you, you select that particular spell checker, that particular spelling for a word, and the desired action is then performed. This is an example of the integrated help, while the add-on is the help menu that is being provided at the end of every application menus. So you click the help menu and then different questions are there or you write your question and different answers are then generated, which may be or may not be related to the query or the problem you are facing. So integrated help is far better as compared to the add-on help. The next type of design issue is the error information handling. Error messages and warnings are bad news delivered to users of interactive systems when something has gone wrong. At their worst, error messages and warnings impart useless or misleading information and serve only to increase user frustration. In general, every error message or warning produced by an interactive system should have some of the characteristics. For example, the message should describe the problem in jargon that the user can easily understand. The message should provide constructive advice for recovering from the error. The message should indicate any negative consequences of the error so that the user can check to ensure that they have not occurred. The message should be accompanied by an audible or visual cue. That is, a beep might be generated to accompany the display of the message, or the message might flash momentarily or be displayed in a color that is easily recognizable, as the color is easy to be observed. The message should be non-judgmental. That is, the wording should never place blame on the user. Because no one really likes bad news, few users will like an error message, no matter how well designed. But an effective error message philosophy can do much to improve the quality of the interactive system, and this will significantly reduce user frustration when some problem occurs. So error information handling should be done in very careful manner so that user can understand what activities of user have generated the error and how that error has to be removed. The fourth common design issue is the command labeling. The typed command was once the most common mode of interaction between the user and the system software and was commonly used for applications of every type. But today, the use of a window-oriented point and pick interfaces has reduced reliance on typed commands. But many power users continue to prefer a command-oriented mode of interactions. So, the command labeling, the labels should be properly define the action or the response that will be generated from the system. So in this way, user will have an understanding and an ease of use of the interface that what command should be given by either mouse click or by using some mnemonics which could bring the required results to the user. So these are the four very common design issues which needs to be addressed before finalizing the software. Now the user interface design has been completed here, and now we have to move towards the next type of design, which is the component level design. This is the fourth subcategory of software design phase. Now we have to see what is the component level design. Component level design, which is also known as the procedural design, occurs after data, architectural and interface designs have been already generated. The intent is to translate the design model into operational software. But the level of abstraction of the existing design model is relatively high, and the abstraction level of the operational program is quite low. The translation can be challenging, opening the door to the introduction of subtle errors that are difficult to find and correct in later stages of the design process. Data, architectural, and interface design must be now translated into the operational software. In order to accomplish this, the design must be represented at a level of abstraction which is close to the code. Component level design actually establishes the algorithmic detail required to manipulate data structures, effect communication between software components through their interfaces, and implement the processing algorithms required for every component. So in this case, we actually, within the component level design, we establish the algorithmic detail of every required component. That means every function that has been designed for the software. Now you have to write the algorithms for every defined function. We have to explain the effective communication between the software components and user, and then implement those processing algorithms that we have defined for all the functions. So this is what the component level design is. Now, who performs or who designs the component level design? A software engineer generally performs this component level design. You have to be able to determine whether the program will work before you are going to build it. The component level design represents the software in a way that allows you to review the details of the design for correctness and consistency with earlier design representations. It provides a means for assessing whether data structure, interface, and algorithm will work or not. Now, what are the steps in designing the component level design? Design representations of data architecture and interfaces form the foundation for the component level designs. The processing narrative for every component is translated into a procedural design model using a set of structured programming constructs. Graphical, tabular, or text-based notation are commonly used to represent the design. Now, what is the end product of this design type? The procedural design for every component represented in a graphical, tabular, or text-based notation is the output. It is the primary work produced during this component level design. Now, how it is ensured that what you have generated is correct? A design walkthrough or inspection is then conducted on the component level design. The design is examined to determine whether the data structures, interfaces, processing sequences, and the logical conditions are correct and will produce the appropriate data or control transformation allocated to the components. Components here means the functions during earlier design steps. Now we have to see what is the structured programming. you have been using different structured programming tools in which you give structure to your programs. The foundation of component level design were formed in the early 1960s and were solidified with the work of different researchers. In late 1960, some researchers proposed the use of a set of constrained logical constructs from which any program can be then formed. The constructs emphasize the maintenance of functional domain. So, the structured programming actually highlights the use of functions or dividing the program in different small units known as the functions. So, every construct had a predictable logical structure, was entered at the top and exited at the bottom. So, every function has a structure. It enters at the top and exits at the bottom, enabling a reader to follow procedural flow very easily. So generally, the structured programming consists of different constructs. So the constructs are actually the sequence, condition, and repetition. Here you can see these are the different constructs. This represents the sequence of different steps. This represents the condition. If the condition is true, it will go in one direction. If it is false, it will go in another direction. And then this is the selection, where you can use switch for the selection. Different cases are given and then every case generates one response. And then this is the repetition that shows the loops in which something or some sequence of steps need to be repeated in defined sequences. So the sequence elements or the sequence implements the processing steps that are essential in the specification of any algorithm. So the sequence means certain steps need to be followed one after another in a sequence. While the condition provides the facility for selected processing based on some logical occurrences. So condition means if something is true, some other step of actions need to be performed, and if something is wrong, then some alternative sequence of actions need to be performed. While the repetition allows for the looping. You have different types of loops such as for loop, while loop, do-while loops. So that means some sequence of actions are performed in specific number of times. So these three constructs are fundamental to structured programming. That means they are an important component level design techniques. The structured constructs are proposed to limit the procedural design of software to a small number of predictable operations. The use of a limited number of logical constructs also contributes to a human understanding process that psychologists generally call as chunking. A picture is worth 1,000 words, but it's rather important to know which picture and which 1,000 words. There is no question that graphical tools such as the flowchart or box diagram provide useful pictorial patterns that readily depict procedural details. However, if the graphical tools are misused, the wrong picture may lead to the wrong software. So there are two types of graphical design notations that are commonly used. One is the flowchart and the other one is the box diagram. Flowchart is the most commonly used. Flowchart is quite simple pictorially. A box is used to indicate a processing step. A diamond generally represents a logical condition and arrows show the flow of control. So here you can see this is the flowchart diagram. So these show the sequence of activities. This is actually a diamond. Here you can see diamond shows the condition. So either condition is true or false, so you can move on either of the side depending on the condition. The first structure is the sequence of instructions, shows the sequence as two processing boxes are connected by lines of control. Here you can see this is the sequence when different boxes are connected in a sequence. Condition, also called if then else, is shown as a decision diamond that if true causes then part processing to occur and if false invokes the else part processing. So here you can see this is the if then else. If the condition is true, one part is executed, and if the condition is false, the other part or the else part is executed. Repetition is represented using two slightly different forms. The do-while tests a condition and executes a loop task repeatedly as long as the condition holds true. A repeat until executes the loop task first, then tests a condition and repeats the task until the condition fails. This is do-while and a while do. So here you can see the repetition is shown here. In one case, in do-while case, statements are executed first and condition is checked at the end. While in while do sort of repetition, condition is checked first and then statements are executed later on. The selection or the select case, here you can see this is the select in which you normally use in case of switch statements. So this is known as the selection or the select case construct, as shown in this diagram, is actually an extension of the if then else. A parameter is tested by successive decisions until a true condition occurs and a case part processing path is then executed. So in selection you provide different conditions on the basis of whatever condition matches to your requirement, that specific sequence of instructions get then executed. Not all the sequence are executed. So this is an alternative to the if then else. So the second graphical design notation is the design box or the box diagram. It is evolved from a desire to develop a procedural design representation that would not allow violation of the structural constructs. So different structures are used or different boxes are used to represent the same structures. For example, if you are to draw the sequence of instructions, similarly this is the sequence. Here you can see in boxes we have represented, but when you are to form it in shape of a box diagram, so this is how you can draw the sequence: a big box and then small boxes one after another connected to one another. So this shows the sequence of instructions similar to this one. So first sequence of instructions are written here in first box, then second they are to be executed one after another. So this is the box diagram for sequence. Now the second is if then else. For example, if you have to draw the condition if then else. So again a box is drawn like this, a big box, and then the box is segregated horizontally in two parts like this, and here you have to then further divide it diagonally like this. So here you will have to write the condition. If the condition is true, so true path is here, and if the condition is false, false, or the else part is written here, and you then separate the sequence of steps under true or false. So this is the then part. If condition is true, then this, but if condition is false, so here it is the else part. So this is how we draw the if then else or the condition statement. Similarly, if you have to draw the repetition, such as this one, this is the repetition, while do while sort of. So if you have to draw the repetition, again a box is drawn for two type of repetitions, while do and do while. Then another small box is created inside this one. This is the loop condition. Here you have to write down the loop condition, whatever condition is fixed, and then here it is do while loop. That means first you have to write the sequence of instructions, and then you have to write then you have to check the condition, while its alternative is the while do. So here again I would draw the similar box like this and a small box like this in order to distinguish between both of them. So repeat until part. So first the sequence of instructions have to be executed, and then here the while condition is to be checked. So this is this one. First one shows the while do box, and the second one, this one shows the do while. First sequence of instructions will have to be executed, and then the condition is verified or checked. So in this way, repetition, this diagram represents these two boxes, either do while or while do. And similarly, other constructs are used, other type of boxes are used to draw the selection diagrams. The fundamental element of the box diagram is the box, as we have said or have seen and drawn different types of diagrams. The second notation, the second structured programming design notation is known as the tabular design notation, in which we have to draw the tables. In many software applications, a module may be required to evaluate a complex combination of conditions and select appropriate actions based on these conditions. So decision tables provide a notation that translates action and conditions in a table form. The table is difficult to misinterpret and may even be used as a machine-readable input to table-driven algorithms. So the common use of tabular design notation is in case of decision tables that are commonly used. The one drawn in this picture, you can see this is the decision table. How the table is organized? The table is divided in 4 sections. The upper left hand quadrant, this one, the upper left hand quadrant contains a list of all the conditions. As you can see, set of conditions are written in the top left quadrant, while the lower left hand quadrant, this one, in which a series of actions are mentioned or written. So the lower left hand quadrant contains a list of all the actions that are possible based on the combinations of conditions mentioned above. Now the right hand quadrant forms a matrix that indicates conditions, combinations, and the corresponding actions that will occur for a specific condition. So these are then different rules. Here, as you can see, different set of rules are written, and for which condition, which specific action need to be taken place, that are then marked either true or false or in shape of tick marks. Therefore, every column of the matrix may be interpreted as a processing rule. This is commonly used in artificial intelligence when rules and conditions are to be matched in order to take appropriate action. So tabular design notation or decision tables are used very commonly there. Now, which design notation should be used, or which is more appropriate for a specific type of software design? So there are certain comparisons. So on the basis of these different parameters, you have to select the appropriate design notation that we had just discussed in the previous slide. So the first comparison parameter is modularity. The design notation should support the development of modular software and provide a means for the interface specification. So whatever design enhances the modularity or divisioning of the software in different small modules. So whatever design notation enhances modularity, that particular design notation should be used. The second parameter for comparison is the overall simplicity. Design notation should be relatively quite simple to learn and relatively very easy to use and generally easy to read. So simplicity should be kept as a parameter when reading and designing the notations. The next factor or comparison parameter is ease of editing. The procedural design may require modifications as the software process proceeds. The ease with which a design representation can be edited can help facilitate each software engineering task. So the more easy it is to change the notations or the construct within the design notation, the more easy it is to handle. So the ease of editing should be the parameter, as you are not able to draw the design complete in one go. It requires iteration. So the ease of editing can help to draw an iterative design. The next factor for the comparison is machine readability. Notation that can be input directly into the computer-based development system offers a significant benefits. So if it is machine readable, that is a plus point for the design. Maintainability is the next comparison factor. Software maintenance is the most costly phase of the software lifecycle. Maintenance of the software configuration nearly always means maintenance of the procedural design representations. So maintainability should be a factor. The more software requires maintenance, the more cost is incurred on that particular software. So the maintainability factor should be kept in the design notations when you are going to select one of them. The more software is procedural, the more components are provided, the more functional units are provided, the more easy it is for the design notation to be maintained. The next comparison factor is the structure enforcement. The benefits of a design approach that uses structured programming concepts have already been discussed in the previous slides. So design notation that enforces the use of only the structured constructs promote good design practice. So the construct that we have already discussed, such as repetition, if then else, diamond notations, the loops, etc. So if your design notation is to implement such structures, so that would bring benefit to the overall software. Automatic processing is the next comparison factor. A procedure design contains information that can be processed to give the designer new or better insights into the correctness and quality of a design. So the more functional units are there, the more functions are there in the software, the more easy it is to understand the software. The designer will have a better insight into the software. So such insights can be enhanced with reports provided through software design tool. So you can build the designs, or you can build the design notations using some automated tools which will be helpful in direct machine readability of your designs. The next comparison factor is the data representation. The ability to represent local and global data is an essential element of the component level design. Ideally, design notation should represent such data directly. So if local and global variables can be easily represented using any of the design notation, so that particular design notation is considered better. The next factor is the logic verification. Automatic verification of design logic is a goal that is paramount during software testing. Notation that enhances the ability to verify logic greatly improves testing adequacy. So, if the design notation itself verifies the logic of the program, so the testing part, which we'll be discussing in the coming chapter, testing is a phase of software engineering, which is the last phase of software engineering in software development. So if the design notation itself verifies the logic of the code, so the testing phase becomes quite easy, since testing is quite exhaustive task. So logic verification through the design notation simplifies the task of the tester. Well, the last verification comparison factor is the code to ability. The software engineering task that follows component level design is code generation. So after designing, the next phase is the code generation. Notations that may be converted easily to source code results effort and error. It helps in reducing the errors being generated and also reduces the time and effort of the developer. So if your design notation is machine readable, that verifies the logic itself, that enforces the different structures being used in the code, and it is easily available and readily available to be coded either automatically or manually. So this will reduce the effort, time and cost of the developer. So coding will become easy if your design notation is code to ability having factor. That is all for now. We'll continue our discussion in this chapter in the coming lectures as well. In today's discussion, we had a detailed discussion on component level design, and component level design actually refers to splitting of of your code in different manageable units or functions or components. Structured programming facilitates designing component level designs for the softwares. As the structured programming says, your program should be divided in manageable units, which we generally call as functions, and every function has a starting and ending point. So the more functions are provided in your software, that means the more task is manageable, the more activities can be easily managed, error can be easily removed, and error propagation can be highly reduced. So here we use different design notations to highlight different constructs within your functions. So different design notation that we have discussed are the flowcharts, either among the graphical design notations. So among the graphical design notation, there are two types. Either we can use the flowchart, which is very commonly used, or you can use the box diagrams. Box diagrams are quite tricky, so you can use the flowcharts, which is very commonly used. And another graphical design notation is the tabular design notation, which is commonly used in artificial intelligence, in which conditions, rules, and actions are written in shape of decision tables. So this is how we divide the important constructs within different components of the software. Components here means the functions of the software, and represent them using pictures. Diagrams are easy to read, diagrams are easy to understand instead of words. So if the image is clearly depicting how actions are going to be performed in the software, it will be easy not only for the designer to understand the logic of the program, but also to the user to understand how software will perform his required actions and in what sequence. That is all. I thank you all.